All right, welcome to lecture 15 for Intro to Machine Learning. This is a course at Northeastern University, DS 4400. Now, today we're going to go over the decision tree, random forest, boosting. So, this is Professor Wu. Let's get started. Now, previously, we've gone through quite a few classification models. So, Um, and in general, the classification models can be divided into parametric and non-parametric. Parametric is when you essentially have a function you're trying to learn, and there are these thetas, and you want to learn the theta. Once you learn the theta, you essentially know the function. And over here for SVM, we're trying to find the weights, right? So ideally, you want to find the weights. Once you know the weights, then you know how to do the classification. Non-parametric models are different. It's not like there's a function you're trying to learn, right? Instead, you can perform classification a different way. Last time we did this called the k nearest neighbor. Basically, there was no function. You just pick the nearest neighbors and set your label to be the same label as the nearest neighbors, and that's it. So you can see that non-parametric models, you're not trying to learn a function or anything. You basically use the information within data to make decisions. So last time we learned the k nearest neighbor. Today we're going to learn another algorithm, probably one of the most famous non-parametric classification model called decision tree. So let's get started. Now, in order for us to understand decision tree, you need to understand two main concepts: entropy and conditional entropy. Last time in information theory, we covered entropy. Entropy is essentially the expected information. So we have gone through what the definition of information is. Right? So this is the equation for information, and the expected information is entropy following this equation. Now, entropy is the average information. You can also think of it that way, kind of like the average. Now, the second concept you guys need to understand is this thing called the conditional entropy. And we have not yet learned this concept. And the equation for conditional entropy is similar to entropy, where you have probability of xy log. So the only is a joint distribution. The only difference is conditional, probability y given x. Okay, so this is kind of the information after you know x, so that you can kind of picture it that way. Now, this is the equation for conditional entropy. We can use Bayes' rule for this joint distribution, which according to the Bayes' rule, it is just the conditional times p of x. So from the Bayes' rule, you should be able to see how they are the same. Okay. Now, because over here is summing over y, we can move p of x outside, essentially put it here. So this is equal to this. And we're going to use this form as the general form which we're going to measure conditional entropy. Now, this looks like kind of like a intimidating problem, but it isn't. When we're finding entropy, what you do is you let p of x equal to something, right? And then you sum up all the possible y's given x. And then you let p of x equals to something else, then you repeat this process. I think this will be easier to understand this equation once we've done some exercise. So let's start with a quick review with entropy. Okay, so entropy, I told you previously, is the expected information. And this is the equation for information. Now, I want you to pause the video and see if you can do this very simple case. Okay, pause the video and we're going to move on. Now, okay, so expected information is just the equation of information p of x, and you're trying to sum them all up. That's what expectation means. So what is so P of x? There are two possibilities, right? One is this one, which is 9 over 14. This one is 5 over 14. So these are the probabilities. So the first one, we're going to have 9 over 14, 9 over 14. You see how the probability goes here? And then the probability goes here. Now, remember, this is 1 over, right? Notice I don't have 1 over. That's because there's a negative sign here. When you have a log of 1 over x, it's equivalent to minus log of x. Okay, that's what I did here. Now, so I took the first one, 9 over 14, 9 over 14. And now I'm going to take the second one, 5 over 14, 5 over 14. And now we know that the entropy is approximately this. Hopefully, you're able to get the same thing because we already calculated entropy. Now, the next thing we want to calculate is conditional entropy. So practice calculating conditional entropy. Now remember, the equation we want to use is this, right? So let x be the outlook. So if you have the outlook, which you have three possibilities, and then y, so this is x, y is going to be whether you play golf or not. So you can then make conditional distribution out of this and plug them in here. So take a second, pause the video, right? Pause the video and see if you can do this. Okay? So we're going to pause the video because we're going to move on. Now, this right here is the equation of how you would have calculated that previous thing. So x, right? We're trying to find probability of x, conditional entropy, which you pick a x. So we start with x is equal to sunny, right? If we know x is sunny, then we multiply this by all the combination summation. So this, we're going to put all the combinations here. So notice, given x is sunny, given x is sunny, given x sunny, given x is sunny, right? So we're going to do probability of y equals to yes, given x is sunny, and then here's the information portion. And then probability y is equal to no, given is sunny, and here's the information. So that will give us the very first one, all the sunny cases. Next, we have a second case, which is overcast. So given overcast, notice every one of them is given overcast. So given is overcast, then you're going to sum up all the possibilities. Y equals to yes, and the information of y equals to yes, along with y equals no, and the information. And lastly, we will do rain, right? So the last one. So to calculate conditional entropy, like you want to study how we calculate conditional entropy this way. If you do all the math out, right, you plug all the probabilities in, because yeah, all the probabilities in, this is what you should get. Okay, so here's another one. So we did it again, right? Over here is outlook. Here's temperature. Given temperature, can we predict whether somebody is playing golf or not? So let's say over here is the equation. So try again. Okay, so now that you have seen us do it together, see if you can do it again. Okay, pause the video and I'll move on. Okay, so uh, what are we? Now we want to calculate conditional entropy, probability. So we'll start with this x and this is y this time, right? So temperature, given that temperature is hot, right? Then what's the probability? Yes, and what's the expectation? No. And then we do hot, right? Given that it's hot, and then it's given it's cold. So we did hot, now it's cold. And then we basically go over probability yes, given it's cold, yes, given it's cold, no, given it's cold, no, given it's cold. So what you want to do is look at this and make sure you understand how this and this is equivalent, okay? And then how this fits into the picture here. So hopefully you had better success for the second example. Using entropy and conditional entropy together. Now, remember intuitively that entropy is the expected amount of information for an event of multiple outcomes. Entropy is based on randomness. The more random, right, the more information exists in the system. So if something that's real, remember I was saying how when things are unlikely, then like the state of Florida getting destroyed, right? That's very unlikely, and therefore that statement it contains a lot of information. Now, so if entropy is you can picture it kind of like the average information, conditional entropy is the residual entropy. You can picture it that way. So conditional entropy is when given x is known, right? So therefore, if more information is known, then less information is left over. So that's why we call conditional entropy a residual entropy. After some information has been revealed, right? Once something is revealed, the amount of information left over is always going to be equal to or less than the original. So if you originally, y has some kind of like entropy in there. Now, some information is revealed, x is going to be revealed. After x is revealed, well, there's less information left, right? Therefore, the original amount of information, the original amount of entropy, average information, is going to be greater than the leftover. The amount of information gained by knowing x. So after you know x is the difference between the original and the conditional. Okay, so we have the original, and this is the what's left, the amount of entropy left. Original entropy and the entropy after x is revealed. So if this right here, one is like the original and one is the leftover, then the difference, right, must be the amount of information gained. So how much did your information gain from having X being revealed? Of course, the bigger the information gain, right, the more information X is telling us about Y, right? If if the information gain after X is huge, that means there's not much information left about Y, and therefore like X must tell us a lot about Y, right? And this is called the information gain. The difference before and after X was like given, right? So, which factor give us more information on playing golf? Here it is. So, which one give us more, right? So now we can essentially calculate the original entropy, right? So this is y, and then y given x1, y given x2, right? So I want you to like pause the video, try not to look at this, pause the video and calculate the residual entropy, right? As well, sorry, calculate the information gain. So by knowing the outlook, how much information was gained, and by knowing the temperature, how much information was gained. So, so see if you can like identify that. Well, from that, I hope you kind of have a general idea now how decision trees might work. Well, the way it works is maybe we have a table like this, and we're trying to predict whether a person is going to play golf or not, yes or no, right? So, given the past history, right, based on weather patterns, the decision tree, what it does is you start with one of them. You pick one, And then after you've split into the various categories, right? Then if if for example overcast, right? Let's look at overcast. Overcast, overcast. So notice overcast only has yes, right? So at that point, you know the decision, right? If it's overcast, you made the decision. However, if it's sunny, then you need to consider other things, such as whether it's windy or not, right? Or if it's rainy, you need to consider whether it's humidity. So with the decision tree, the key, the name of the game is essentially deciding which attributes you should pick first. How do you pick the first one? And then how do you pick the second one? How do you pick the third one? Right? So that's how decision trees are constructed. At each layer, the decision tree picks an attribute, right? You pick one of the features and then move on to the next layer. So the natural question is, how do we pick which feature should be picked first, right? Well, now that I've given you so many like hints, I hope you can guess that we want to pick the feature that essentially give us the most information. The most information gained after you've gained after something is revealed, right? And we already know how to calculate the information gain from like our previous practice. So okay, so let's take a look. These are all the features. Which features should we pick first? Given the data table, let's see, where's that data? Yeah, given this table. So let's take a look at this table, right? I want you to essentially, so there are four of them: outlook, temperature, humidity, wind. See if you can calculate the information gain for each of them. So pause the video, see if you can calculate the information gain. And like over here, I showed you the information gain. So what you want to do is not look at it, see if you can calculate the information gain yourself, and then see if you get like the same result as I did. Okay, so that's the information gain. And then you will see, ideally, you'll see that the outlook is the first thing you want to pick. Okay, so from here, uh, yeah, let's assume you paused the video already and that we've moved on. So you will see that over here, the information gain for outlook is the largest. And that's why we decide to branch out with outlook first. Now, after you split the branch, what do you do then? Well, for the case of overcast, I showed you previously that there's only one option. The option is yes. If it's overcast, it's always a good time to play tennis, apparently, or golf, right? But what if it's sunny or rainy? Well, if it's sunny, right, then you need to create a smaller table. So these are the sunny ones. These are the sunny ones. This is sunny as well, and this is sunny. So essentially, we have yeah. So given sunny, essentially we take all these and create another table. This will create a table where the outlook is always sunny, right? And assume that sunny is already known. Now you have a smaller table where it's temp, humidity, wind, right? So, so that was for sunny. You will create a smaller table, but I don't think I put that here. Let me yeah, I didn't put that here. Let me do the other one. So the outlook, what if it's raining? The other one's raining. So the raining here, these are rainy. These are rainy, and that's it. So altogether, there's five of them, right? So there's five of them. So you essentially create another table. And given that it's raining, so you're not going to look at this column anymore, right? Now you can again use this smaller table to calculate the information gain, right? What is the information gain for each one of them? And from there, you will again pick another one, right, with the most information gain. And again, you would go to the next layer. Then you go to the next layer, right? So that's basically how decision trees are made. It's all completely based on the concept of information gain, like um, essentially conditional entropy and information gain. Now, decision tree is a very popular algorithm. For a long time, decision tree has been one of the most popular. In fact, it's pretty easy to implement, and it does a pretty good job, right, on mostly simpler database. And it also tells you which features are important. So in this case, it's saying the outlook is the most important, and the winding and humidity are less important, right? So decision tree essentially tells you which feature give you the most information. Okay, so that's decision tree. From decision tree, it leads us to the concept of like bagging. Which is part of ensemble methods. Like so, next up, we're gonna learn what is bagging and how we move from a tree. So this is a tree to an entire forest. Okay, so so let's move on to ensemble methods and bagging. Ensemble method is a machine learning strategy that essentially combines multiple classifiers on the same data to improve performance. Okay, so instead of using one classifier, it's combining the result of multiple classifiers. Now, ensemble method can be employed parallel, so they are doing simultaneously, or you can do them, or you can do them in serial. So you train one, take the output of one, train the other one. All right. If the algorithm employed is parallel, it's called the bagging strategy. Ensemble method can be employed also in serial. This implies that we must train multiple classifiers, one after another. We take the output of one and put it into the input of another one. If the algorithm employs a serial strategy, it is called boosting. So that's the difference between bagging and boosting. For today, we're just gonna focus on bagging because this leads directly into random forest. Okay, so bagging and random forest. In bagging, you use a random subset of the data. So imagine if you have like 10,000, right? And instead of 10,000, what you do is you maybe pick 5,000 randomly, right? You just pick 5,000. And then you train a tree, a decision tree. Now you pick another 5,000. You train another tree. We're going to call this tree 2, tree 1. So you can imagine you can have all the way to tree 100. You have 100 trees. Each one of them use different data to essentially train it. And therefore, each one of the trees are slightly different, right? Because they use different data, they might actually come to different decisions, right? Therefore, what you can do at this point is use all the trees simultaneously, and the trees are going to give you a decision. Well, yes, no, yes, yes. And it's going to give you multiple labels, right? And then what you do is you just do the majority vote, right? So the majority vote, and then from here, this drastically increases the capability of decision trees because instead of just one classifier, you're using like maybe 100, right? And 100, and then their average result, it's a lot better than just one tree. Hence, they call this like random forest. So it's a whole forest, which kind of makes sense. So the random forest classifier in sklearn code is just one line, very easy, and it will do like classification for you. Now, what I want you to do is essentially use this table that we have been working with. write the code that generates this tree. Okay, try to write your own random forest. Try to write your own decision tree. Once you have written a decision tree, then what I want you to is generate an entire forest. Once you have a whole forest, you should be able to get really, really accurate results for prediction. So, so I think that's it. Yeah, I will see you in the next class.